Namaskaram everyone. It's my pleasure in welcoming you all for another session on mathematics. And today, as you know, Shastri Madam has started complex numbers. She's going to make the complex numbers easier for you. And today is the third lesson. She will be dealing with the amplitude, modulus amplitude form of complex numbers. Over to you, Usha Madam.
Madam, thank you so much. Good morning, everyone. I'm here with the next session of complex numbers. In this session, we will try to go with what is modulus of a complex number, and then we will get into the main topic, that is modulus amplitude form of a complex number. Now, the topics for today: finding the real and imaginary parts for a given complex number. Like first, we will reduce the given complex number into A plus IB form. This we were talking about in the previous sessions. This is a continuation of the topic, what we dealt in the previous sessions. Then modulus of a complex number, amplitude of a complex number, Cartesian coordinates and polar coordinates, and representing a given complex number in modulus amplitude form. So just to go with modulus amplitude form, you need to understand the two terms, that is modulus and amplitude of a given complex number. Okay, we'll look into that. Now to start with, we'll take up a problem first. Find the real values of theta when 3 plus 2i sine theta by 1 minus 2i sine theta is purely a real number, purely an imaginary number. Now children, as we were talking again and again in the previous sessions, we always, when a problem is given to you, first we will be checking whether you have I in the denominator, isn't it? If you have I in the denominator, first it is our foremost, the first prerequisite to get rid of I in the denominator. So for that, we were multiplying and dividing with a conjugate. The same concept we will do first. Then we will discuss what is purely real and purely imaginary. So we are given with 3 plus 2i sine theta by 1 minus 2i sine theta. First, we are trying to reduce into A plus IB form. So we are just multiplying and dividing with the conjugate of the denominator. Isn't it? The conjugate is 1 plus 2i sine theta. Then we have in the denominator, it is A plus B into A minus B form. So 1 square is 1 minus 2i sine theta whole square. And in the numerator we have 3 into 1, which is 3, plus 3 into 2i sine theta, that is 6i sine theta. 2i sine theta into 1 gives you 2i sine theta. And 2i sine theta into 2i sine theta gives you 4i square sine square theta. Wherever we have I square, we will try to replace it with minus 1, because I square is equal to minus 1, isn't it? So you have 3 plus 6i sine theta plus 2i sine theta, which is 8i sine theta, 4i square. I square is minus 1. So you're getting it as minus 4 sine square theta divided by 1 plus 2 square is 4. I square is minus 1. So minus in, and this minus is giving you plus and sine square theta. Next, we have it as 3 minus 4 sine square theta. See, this term in the numerator, it has got no I in that, isn't it? So we can separate it as real part. 3 minus 4 sine square theta by 1 plus 4 sine square theta plus I into this 8i sine theta we have. So we are taking I out and we are writing it as 8 sine theta by 1 plus 4 sine square theta. Now here children, till now, we have reduced the given problem in A plus IB form. Now let us talk something about purely real number and purely imaginary number. Now what is purely real? All this time in the previous classes, what we were looking into were real numbers only. That means there is no I term in the given number, isn't it? That means when a number is purely real, imaginary part should be equal to 0. When I say it is purely imaginary, that means the real part should be equal to 0. So now we will take up the first bit, purely real. Purely real means the imaginary part is 0. What is our imaginary part? It is 8 sine theta by 1 plus 4 sine square theta. We are equating it to 0 because it is purely real, right? Now go for cross multiplication. You will have 8 sine theta is equal to 0. 0 into this gives you 0, isn't it? So 8 sine theta is equal to 0. So sine theta is 0. When sine theta is 0, theta takes a value as n pi. We are writing in the general form. Likewise, you have purely imaginary. Purely imaginary, it means that the real part is 0. What is our real part? It is 3 minus 4 sine square theta by 1 plus 4 sine square theta. We are equating it to 0. And on cross multiplication, you will be getting 3 minus 4 sine square theta is equal to 0. Further, I can write sine square theta is equal to 3 by 4, or sine theta is root 3 by 2. And in the general form, we can always write theta is equal to 2n pi plus or minus pi by 3, right? So find the real values of theta. So we are finding out all the real values possible, and we have given in the general form because trigonometric ratios are periodic. So the same value may be repeated for many different measures, isn't it? So that's the reason why we are giving the answer in general form. This general form you have learned in your first year, children, in general solutions. Now we'll go with another problem. Find the real values of x, y if x minus 1 by 3 plus I plus y minus 1 by 3 minus I is equal to I. Here again, see, you can do this problem in two different ways. One is taking each term separately, getting them into a plus IB form and then solving. Or if you can observe carefully, the two terms what you have here, they have got the denominator parts. If you just observe, they are conjugates of one another, isn't it? So directly you can take LCM and you can start solving. So we are given with x minus 1 by 3 plus I plus y minus 1 by 3 minus I is equal to I. We'll take the LCM, that is 3 plus I into 3 minus I gives you 9 minus I square, because it is in the form of a plus b into a minus b. Then you have in the numerator x minus 1 into 3 minus I plus y minus 1 into 3 plus I is equal to I. We'll go for further expansion. You will have it as 3 into x, that is 3x. X into minus I is minus xi. Minus 1 into 3, which is minus 3. Minus 1 into minus I is plus I. Then you have plus y into 3 is 3y. Y into I is yi. Minus 1 into 3 is minus 3. Minus 1 into I is minus I. Whole divided by. This I square is minus 1, children, isn't it? So minus 1 into this minus, it gives you plus. So 9 plus 1, 10 in the denominator, which is equal to I. Then I and minus I, they are getting cancelled. Right? We will try to club all the terms without I in one bracket and with I in the other part. You will have it as 3x plus 3y. Minus 3 and minus 3 is giving you 6. So 3x plus 3y minus 6 divided by 10 is your real part, plus all the I terms now. Minus xi plus yi, isn't it? Out of that, I am taking I common. Then I'll get minus x plus y divided by 10 is equal to I, right? So we got the problem in A plus IB form. Then observe this carefully. You have some x plus IY equal to some I. That means two complex numbers are equated. So when they are equated, it means the like terms should be equal. Here, comparing the like terms on both sides, we have 3x plus 3y minus 6 by 10 is equal to 0. Why this is 0? Because on your right hand side, you have only I. I is nothing but the real part is missing. So 0 plus I into 1, isn't it? So 3x plus 3y minus 6 by 10 is equal to 0 and minus x plus y by 10 is equal to 1. Then we'll go for cross multiplication, which gives you 3x plus 3y minus 6 is equal to 0 and minus x plus y, when this 10 is multiplied, it goes to the other side, which is equal to 10. Then we'll try to solve these two equations, children. The first equation is 3x plus 3y is equal to 6. And the second equation what we have is minus x plus y is equal to 10. Now just to solve it, we'll go by elimination method by multiplying the second equation with 3. We have 3x plus 3y is equal to 6. The first equation is not changing. The second equation, you will have it as 3 into minus x is minus 3x plus 3 into y is 3y is equal to 3 into 10, which is 30. 3x and minus 3x, they get cancelled. Then you will have it as 6y is equal to 36. When 6y is equal to 36, it means that y is equal to 6. When you put y is equal to 6 in one of the equations, right? If I put y equal to 6 here, what happens? Minus x will be equal to 4. Then x will be equal to minus 4, right? Therefore, x is taking the value as minus 4 and y is taking the value as 6. Now, the next important concept what we are taking up is modulus of a complex number. Modulus of a complex number. Let z is equal to a plus ib is a complex number what we are taking. Then the non-negative real number root of a square plus b square is called modulus of z. So modulus of z is defined as square root of this a square and b square. Both are real numbers, a and b are real numbers, but this ib is imaginary part. Because of this I multiplied with b is giving you imaginary part. Otherwise, a and b, when you take it separately, they are real numbers. This is what we have seen in the first session of complex numbers, isn't it? So when we square any two real numbers and add, definitely you are going to get non-negative real number only. In real numbers, when we square a negative number, it gives you positive. So both positives added will always give you a positive. So the non-negative number root of a square plus b square, when z is equal to a plus ib is called modulus of a complex number. We denote it with parallel lines for z, right? We read it as modulus of z, or we can always say it as r. R is nothing but the modulus of a given complex number. Now, when modulus of z is equal to 0, when mod z is 0, it implies that the complex number itself is becoming 0. Now, just we will try to analyze. Now, if z is equal to 0, that means what? You have a as 0, b also as 0, isn't it? 0 plus 0i. 0 square plus 0 square under root is 0 only. That means when the complex number is 0, then its modulus is also 0. Now, if one of the number is existing other than 0, that means let us take a equal to 1. then you will not get modulus as 0, isn't it? So the real and imaginary parts, if both are 0, then only the modulus will be 0. Then modulus of a given complex number is always equal to the modulus of its additive inverse. Additive inverse we have seen in the first session. A minus multiplied with a given complex number is additive inverse. So modulus of a complex number is always equal to additive inverse of a complex number. It is again equal to conjugate, modulus of the conjugate of complex number. It is again equal to conjugate of the additive inverse of a complex number. Now, suppose let us think that z is a plus ib, what we have taken here. What will be minus z? Minus z will be minus a minus ib. Minus a whole square plus minus b whole square gives you the same thing again. Now, if you take conjugate of a complex number, what is conjugate? A minus ib, isn't it? A minus ib. Again, you take the modulus and check. It is a square plus minus b whole square. It's again root of a square plus b square. So we are taking a relation in general like this. We'll go with the next one, that is z into conjugate of z. Complex number multiplied with its conjugate is nothing but you are taking square of the modulus of complex number. See, z and z bar, that is a plus ib into a minus ib is nothing but a square plus b square. It looks like a plus b into a minus b, right? Then if you take mod z, which is nothing but root of a square plus b square, when you take whole square for that, both will be equal. You can very well take z is equal to a plus ib and verify all these conditions, children. Then if you have z1 and z2 as two different complex numbers, right? You multiply both of them and then take modulus. It is always equal to modulus of the product of modulus of each complex number. That is mod of z1 z2 is equal to mod z1 into mod z2. Then if you are taking modulus of z1 by z2, where z1 and z2 are two different complex numbers, it is always equal to mod z1 by mod z2. That means division of individual modulus. Now, if you take this way, maybe if you have I in the denominator, first you should simplify it, then go for the modulus part. Here, you can, on the left-hand side, you can take numerator modulus separately and denominator modulus separately. So either you calculate by this way or this way, both gives you the same answer. Now we'll see a problem, how to find the modulus of a given complex number. First, we need to simplify the given problem. That's what is the question saying. Simplify 1 plus I whole cube by 2 plus I into 1 plus 2i and find the modulus. Now you are given with 1 plus I whole cube by 2 plus I into 1 plus 2i. We'll take the product in the denominator, children. You just start multiplying. 2 into 1, which is 2. 2 into 2i, which is 4i. I into 1 is I. Then I into 2i is 2i square. Then in the numerator, you have a plus b whole cube form. Then it will be taken as 1 cube plus 3 into 1 square into I plus 3 into 1 into I square plus I cube. This is nothing but a cube plus 3a square b plus 3ab square plus b cube. Now further, wherever you have the powers of I more than 1, we will try to reduce it and we'll try to simplify by substituting either I or minus 1. Now 1 cube is 1, children. This is 1 square is 1, so 3I. Here it is I square is minus 1. So minus 1 into all this is giving you minus 3. I cube is minus I divided by 2i square. I square is minus 1. Minus 1 into 2 is minus 2. So 2 and 2, they are getting cancelled. You are left with 4i plus I, which is nothing but 5i. Okay. Now still further, 1 minus 3 gives you minus 2. Then 3i minus I gives you 2i divided by 5i. There is I in the denominator. So I'm multiplying and dividing with I so that we can remove I from the denominator. Then on multiplying, you will have minus 2i plus 2i into I, which is 2i square divided by 5i square. We will replace that I square with minus 1. Then we have minus 2i divided by minus 5. So I can take minus common and I can cancel in the numerator and denominator. Then we will be left with 2 by 5 plus I into 2 by 5. What is this actually? We have solved or we have simplified the given problem till now, isn't it? Now, the next step is finding the modulus of the complex number. So, modulus of 1 plus I whole cube by 2 plus I into 1 plus 2I is nothing but modulus of 2 by 5 plus I into 2 by 5. As we have seen, the formula for calculation of modulus is root of a square plus b square, that is real, real part. The coefficients a and b. In a plus ib, you are taking a square and b square. Here your a is 2 by 5 and b is 2 by 5. So we will take square root of 2 by 5 whole square plus 2 by 5 whole square. 2 by 5 whole square, which is 4 by 25. So 4 by 25 plus 4 by 25 gives you 8 by 25. Root 8 is nothing but 2 root 2, isn't it? 4 into 2 is 8. So root of 4 is 2. So 2 root 2 by root 25 is 5. Right? So this is what this problem is involving. Writing the problem in a plus ib form and then calculating the modulus. Now we'll go with argument or amplitude of a complex number. Now, first we will see what is principal argument. Let P be any point which represents a complex number Z in the Argand plane. I was mentioning about Argand plane, children. It is something like your Cartesian plane only, but only difference is your x-axis there will be mentioned as a real axis here, and y-axis there in the Cartesian plane will become an imaginary axis in Argand plane. Right? There on x and y axis, we were representing real numbers, but here on the real axis, we will find the real part, and on the imaginary axis, we will find the imaginary number. So let P be any point which represents the complex number Z in the Argand plane, and the angle made by OP. What is this O? O is the origin what we are taking. From O to P, if you join a line, and if that line is taking if it is making an angle with a positive x-axis in anti-clockwise direction, and if that angle is considered as theta, then theta is called the principal argument of Z. The principal argument of Z, and we will mention it as ARG of Z, argument of Z. When this theta always it lies between minus pi less than theta less than or equal to pi. The principal argument of a given complex number will always lie or will always take these values in this interval. Now, if z is equal to x plus iy is a complex number and the principal amplitude theta, then theta is defined as theta is equal to tan inverse y by x. Now, if theta is the principal value of the amplitude of a complex number z, then the general value of the amplitude of z will be given by 2k pi plus theta. See, if you can remember your first year general solutions, children, we had principal value and the general value. In the same way here, we have principal amplitude and the general amplitude. Why like this? See, we are dealing with some trigonometric terms here. Trigonometric functions are periodic. That means the value what you are getting for theta in this interval may also repeat for some other values since the trigonometric functions are periodic. So the general value of the amplitude of Z is taken as 2k pi plus theta, where k belongs to, or k can take any integer value. Now, if amplitude of Z is taken as theta, then amplitude of the conjugate of Z is considered as minus theta. If amplitude for a complex number is theta, then the amplitude of the conjugate of a complex number is always taken as minus theta. Now we'll see Cartesian coordinates and polar coordinates. We will take the real axis, children, then an imaginary axis. Now I'm taking the origin as O. Now I take a point P with the coordinates as X and Y. And in the second quadrant, I'm taking the point Q. Q is minus X comma Y. Here, as you all know, X takes a negative value and Y will be positive. And then in the third quadrant, both the coordinates will be negative. So R is minus X comma minus Y. And you have point S in the fourth quadrant. Here the X will be positive and Y is negative. So S is X comma minus Y. Now we will take OP. As I was mentioning, when I was defining modulus, modulus is nothing but the distance from O to P, isn't it? So OP, I will take it as R. This R is making some angle with the positive x-axis in the anti-clockwise direction. Clock will move in this direction, but we are taking in the anti-clockwise direction, anti-clockwise. Okay, so this is theta. And OP is taken as R. Now, if I drop a perpendicular from point P to the real axis, then it's forming a right angle triangle. Now, just observe this. Tan theta. Tan theta is opposite by adjacent. So, this opposite side, what we are taking is giving you the value Y, because X comma Y. See, this is the distance we are taking on Y axis, isn't it? Or here it is the imaginary axis. So this is Y, and here from origin to this point, I mean the foot of the perpendicular what we have dropped, it will be X. So tan theta is nothing but Y by X. So I can always write theta is equal to tan inverse of modulus of Y by X. Now similarly, we will try to take the angle in the second quadrant. Angle is theta. Now the same distance I am taking, children, in the second quadrant. This is again R. From O to Q, I am taking it as R only. And whatever angle I am taking here, the same angle I am taking. Hope you will observe that. But what is the difference between this angle and this? Here, when you are taking in the anti-clockwise direction, this is theta. Till here, it is theta. Now, from here to this particular point, it is 180 degrees, isn't it? Now, this is theta. Only this part is theta. So I can write this as 180 minus theta. Now, why I should write it as 180 minus theta? From here, the angle is measured till here because we are going in the anti-clockwise direction. So this part should be removed because we are taking only this angle theta. I want you to concentrate on this particular point. So in the second quadrant, I will write it as pi minus theta. Pi minus theta, and if I take the same tan theta here, tan theta is again opposite by adjacent, which is nothing but the same distance what I'm taking. So this is y and this part is x. So tan of pi minus theta is modulus of y by x. So pi minus theta is nothing but tan inverse y by x. This tan of something is giving you pi minus theta is equal to tan inverse y by x. I want only theta value. That means only theta. If I want theta, you send to this side, and tan inverse you can send this way. So theta is equal to pi minus tan inverse modulus of y by x. Now we will try to see the same logic in the third quadrant. In the third quadrant, you have OR. OR is the line what we are taking, and the angle is theta again. See, I am taking the same measure of angle, but only thing is the theta position is changing. First, it is in the first quadrant, next in the second quadrant, then in the third quadrant. Okay. Now in the third quadrant, we will try to observe this carefully. From this point to this point, it is 180 degrees. To 180, you're adding something over here, isn't it? That is 180 plus theta. 180 plus theta is this angle. Okay. So I'm just dropping a perpendicular like what I did previously. Then if you consider this angle, it is again opposite by adjacent. So the angle what we are taking is here, as I told you, since we are moving in the anti-clockwise direction, we are taking it as pi plus theta. So tan of pi plus theta is y by x. Then pi plus theta is nothing but tan inverse of mod of y by x. We want only theta, children. So theta is nothing but minus pi plus tan inverse mod of y by x. Now we'll just move to the fourth quadrant. In the fourth quadrant, again the same measure of angle I'm taking, only the position of the angle is changing. Okay, then OS, as usual, it becomes R, that is the modulus. We are dropping a perpendicular onto the x-axis. Now this time, to make our work easy, I'm coming in the clockwise direction. Clockwise, see, anti-clockwise direction will give you a positive angle. In the clockwise direction, if you move, it gives you a negative angle. And here it is 0. 0 minus theta I'm just taking. So tan of 0 minus theta is nothing but again opposite by adjacent, which is mod of x by y. Tan of 0 minus theta is tan of minus theta. Tan of minus theta is equal to mod of y by x, or I can write it as theta is equal to minus tan inverse mod of y by x. Right? Now we will try to see little more information about this argument of z in different quadrants. Now, if z is equal to x plus iy and theta is equal to tan inverse mod of y by x, then your argument of z, argument is nothing but theta, children. Now, when you are taking the theta value, how it is behaving in different quadrants. Now, when I say x is greater than 0 and y is greater than 0, this should be our first quadrant. Why? Both are positive. Both are positive, isn't it? So, when both are positive, theta will be taken as it is. Now, when x is less than 0 and y is greater than 0, this happens in the second quadrant. In the second quadrant, the same theta we are subtracting from pi. So pi minus theta will be considered in the second quadrant. And when x is less than 0 and y is less than 0, both negative happens only in the third quadrant when you have the value of, the point in the third quadrant, then you will consider theta as minus pi plus theta. And then if you have in the fourth quadrant, you will be taking it as minus theta. Why we are doing all this? We are trying to write the principal amplitude or the principal argument, which is lying between minus pi and pi. We have seen the condition, children, minus pi less than theta less than or equal to pi. Now, in specific, we will try to go with one more condition, argument of z. Now, when I'm taking argument of z, children, x is greater than 0, but y is 0. Okay, in this case, your argument will be taken as 0. And when x is 0 and y is greater than 0, that means a positive value, then you will get the argument as pi by 2. If x is 0 and y is less than 0, then we will take it as pi by 2. And when x is less than 0 and y is 0, we will take it as pi. What is the need of this particular concept? See, if you can remember this, some of the problems where you are taking up some multiple choice questions, they may involve this type of conditions. In that case, you will feel comfortable and it will be very easy for you to calculate in a short time. We will see some properties of argument of complex numbers. Now, argument of z plus argument of the conjugate, its conjugate will be equal to 0 when theta is not equal to pi. Okay, when theta is equal to pi, then it takes the value as 2 pi. Now, if argument of the conjugate when you are taking, it is always equal to minus argument of z. And if theta is not equal to pi is the condition. When theta is not equal to pi, this formula can be applied. Then argument of z1 into z2 bar is nothing but argument of z1 minus argument of z2. You can take this as formula, children. For 2 mark questions, what you have for your intermediate, all these formulae will be useful. Then argument of z1 into z2 is equal to argument of z1 plus argument of z2 plus 2k pi for some k belongs to -1, 0 and 1. This 2k pi we are taking because argument the theta, it is involving some trigonometric functions which are periodic, as we know, we have studied in our previous classes, right? Then argument of z1 by z2 is taken as argument of z1 minus argument of z2 plus 2k pi for some k belongs to -1, 0 and 1. Now, children, I just want to mention something over here. When you are calculating the principal amplitude, you need not take this 2k pi. You are taking this 2k pi when you are finding out all the solutions. Okay. Now, modulus amplitude form or polar form of a complex number. Now, we have seen modulus separately and amplitude separately. Whenever you are given with a complex number, we can always represent the complex number in modulus amplitude form or polar form. Let z is equal to x plus iy be a complex number. Then let us consider P as a point which is representing this complex number in a Cartesian plane. And if P is r comma theta are nothing but the polar coordinates of this complex number. If x and y are the coordinates in the Cartesian plane, then r comma theta will be the polar coordinates. Okay. Then z is equal to x plus iy. This can be represented as r cos theta plus I into r sin theta. Or I can always write this as r into cos theta plus I sin theta. We will, in short, we will sometimes write it as r into cis theta also. Okay. We are calling z is equal to r into cos theta plus I sin theta as polar form, where r is modulus as we know, and theta is the amplitude. Okay. Mod z is root of x square plus y square. So root of x square plus y square is root of r square into cos square theta plus sin square theta. Cos square theta plus sin square theta is 1. So root of r square is r. That means mod z is equal to r, where theta is lying between minus pi and pi. And when you have when you are taking cos theta is, look at this, r cos theta is equal to x, isn't it? Then what will be cos theta? Cos theta will be equal to x by r. But what is r? We have calculated it as root of x square plus y square. So cos theta is equal to x by root of x square plus y square, and sin theta is y by r, which is nothing but y by root of x square plus y square. And we can also write tan theta. Tan theta is y by x. As we have seen in the previous concepts, theta is equal to tan inverse y by x, where you will be getting that from these two terms itself. Now, we will see a problem how to express a complex number in modulus amplitude form. Now, the question is, express the following complex numbers in modulus amplitude form. My first problem is 1 minus I. We will say let 1 minus I is equal to r into cos theta plus I sin theta, because this is the representation what we are taking in the modulus amplitude form for a given complex number. Then try to equate the real part with real and imaginary with imaginary. Then you will have r cos theta is equal to 1 and r sin theta is equal to minus 1. Then you take squaring on both sides for these two children. Then you will have r square cos square theta is 1, r square sin square theta is 1. We will try to add both of them. Then from these two, I can take r square common and I'll have it as cos square theta plus sin square theta, which is equal to 1 plus 1. It is nothing but 2. Cos square theta plus sin square theta is the identity what we have. So this is 1. So r square into 1 is r square. So r square equal to 2. It implies r is equal to root 2. Then cos theta, just to substitute r as root 2 in this. Then cos theta is equal to 1 by root 2 and sin theta is equal to minus 1 by root 2. And the theta which satisfies these two conditions is minus pi by 4. And again, this type of problems we have dealt in our first year general solutions, isn't it? Now, this theta, what we are taking is the principal value. Remember, we are not taking the general solution over here. Therefore, 1 minus I, we need to represent that in modulus amplitude form, isn't it? So 1 minus I will be taken as root 2 into cos of minus pi by 4 plus I sin minus pi by 4. Hope you got this. We have taken 1 minus I, we have equated that to r into cos theta plus I sin theta, which is the modulus amplitude form. We are calling it as modulus amplitude form because we are involving modulus and amplitude both in this. Hope you are able to observe that. Right, children. We will go with one more problem. My next question is minus root 3 plus I. Then we'll say let minus root 3 plus I is equal to r into cos theta plus I sin theta. Then we will try to equate real and imaginary parts. We are trying to compare the like terms on both sides. So you will have r cos theta is equal to minus root 3 and r sin theta is equal to 1. We will square them on both sides. Then r square cos square theta is equal to 3 and r square sin square theta is equal to 1. So we have r square into cos square theta plus sin square theta is nothing but 3 plus 1, which is equal to 4. So this is the identity what we have in the bracket, children. So it becomes 1. So r square equal to 4, it implies r is equal to 2. When r is equal to 2, cos theta is nothing but minus root 3 by 2 and sine theta is equal to 1 by 2. Then the theta what you're taking is 5 pi by 6. Just observe this. The same values you may get many number of times because cos theta and sine theta are periodic. I'm mentioning this point again and again. Since the trigonometric functions are periodic, we are taking only the principal amplitude. Remember that 5 pi by 6 is coming to 150 degrees, which is very much there between minus pi and pi. Okay, so I can write this as minus root 3 plus I is equal to 2 into cos of 5 pi by 6 plus I sine 5 pi by 6. Okay, so this is the representation of a complex number in modulus amplitude form. Now, this type of problems will be given for your IPE exams. Generally, if the question is asked from complex numbers, it will be for 2 marks. Okay, now there is an extension of this in the next chapter, that is the De Moivre's theorem. There we will apply modulus amplitude form and we will write all the values of the given complex number. Now that type of question can be given for 4 marks. That means there again you are using the same concept. If it is given only modulus amplitude form, it will be for 2 marks. If you are asked to calculate all the values, it may be for 4 marks also. Okay. Right. Now the next question, if Z1 is equal to minus 1 and Z2 equal to minus I. Now in the previous problem, we were taking only one complex number and we were trying to write modulus amplitude form. Here we are involving modulus amplitude form and we are doing this problem. We'll try to see this problem what I have taken up now in 2 different ways. Okay, so Z1 is equal to minus 1 and Z2 is equal to minus I are 2 different complex numbers. If you observe carefully, Z1 is purely real, Z2 is purely imaginary. Okay, then you are finding the value of argument of Z1 into Z2. Now children, we will take up the solution. Z1 is equal to minus 1. So let us take minus 1 is equal to R1 cos theta 1 plus I sin theta 1. Since we have 2 different complex numbers, I am taking R1 and theta 1 just to differentiate both of them. Okay. So R1 cos theta 1 is minus 1 and R1 sin theta 1 is 0. Then on squaring on both sides for both the equations and adding, we get R1 square into cos square theta 1 plus sin square theta 1 is equal to minus 1 whole square is 1 plus 0, which is nothing but 1. Now, inside the bracket, what you have is the identity, trigonometric identity. So the value of this is 1. So R1 square is equal to 1. This implies R1 is equal to 1. Okay. Then cos theta 1 is equal to 1, right? And the sin theta, cos theta 1 is equal to, now it should be minus 1 children. So theta 1 is equal to pi and we will take up Z2 is equal to minus I. When Z2 is equal to minus I, if we write it in the modulus amplitude form, we are taking R2 into cos theta 2 plus I sin theta 2. Then on equating or comparing the like terms on both sides, you will have R2 cos theta 2 equal to 0 and R2 sin theta 2 is equal to minus 1. Then R square into cos square theta 2 plus sin square theta 2 is equal to 1. Then since this is an identity which is equal to 1, R2 square is equal to 1. So R2 is 1. Then sin theta 2, we can write it as minus 1. That means theta is equal to minus pi by 2. Now, what is that we need to calculate? We need to calculate argument of Z1 into Z2. We are taking the formula as argument of Z1 into Z2 equal to argument of Z1 plus argument of Z2. We have mentioned this in the previous slide, children. This is the principal amplitude what we are calculating. So this is nothing but pi plus minus pi by 2, which is nothing but pi by 2. The same problem can be solved in the other way also, and this will be little shorter than what we have done here. Now, we know that theta is equal to tan inverse y by x, isn't it? So, argument of z1, directly we will take argument of z1 as theta 1, excuse me. Then theta 1 will be taken as tan inverse of y by x. What is my y over there? Y is 0 and theta is minus, and x is minus 1. Okay, so theta 1 is equal to tan inverse of 0 by minus 1. We have one condition I was mentioning to make our problems easy, isn't it? So look at this, your y is 0, and x is less than 0. So this is the condition what we have. When you have this type of condition, then directly you can say theta 1 is nothing but pi. Okay, then we will take argument of z2 as theta 2. Then theta 2 will be tan inverse of, our y value is minus 1, children, isn't it? Minus I is our z2, minus I, it means 0 plus I into minus 1. So x is 0 and y is minus 1. So theta 2 is equal to tan inverse of minus 1 by 0. Now observe this, your x is 0 and your y value is less than 0. That means this is the condition what you are taking. So theta 2 is equal to tan inverse of minus 1 by 0 can be taken as theta 2 is equal to minus pi by 2. Direct application of these conditions. Okay. So argument of z1 into z2 is equal to argument of z1 plus argument of z2, which is nothing but pi plus minus pi by 2, which is equal to pi by 2. See, this is the advantage of learning the conditions. If you know the condition, within no time you are finishing off. Otherwise, you need to take such a long method, like first you should write it in r cis theta form, then calculate r and theta separately for both complex numbers, then apply the formula. Okay. Now, if the amplitude of z minus 1 is a complex number where z is taken as x plus iy, okay, and you should find the locus of the given complex number. The given complex number is z minus 1. Okay. Now we'll see the condition, children. Let z is equal to x plus iy. Then z minus 1 is given to us. So z, instead of z, we will substitute x plus iy. X plus iy minus 1. We are clubbing all real parts in one bracket. So x minus 1 plus iy is nothing but your z minus 1. Amplitude is given as pi by 2. That means tan theta. Tan theta, what we have is mod of y by x. When z is x plus iy, tan theta is mod of y by x. Then here our theta value, that is amplitude, is given as pi by 2. Tan pi by 2 is equal to y by x minus 1. Then tan pi by 2 is infinity. Infinity can be taken as 1 by 0, right? This is equal to y by x minus 1. On cross multiplication, you will have it as x minus 1 equal to 0. That means x is equal to 1. Not only x equal to 1, if you can observe the value of y, here the amplitude is pi by 2. So the y value what you are taking is always positive. So therefore, we can conclude saying that the locus of the given complex number is x equal to 1 and y is again greater than 0. Now, these are the practice questions for today. We have taken up modulus amplitude form, children. So you can calculate modulus amplitude form for these problems, and then some problems related with argument, and then cis theta form, cos of cos 2 alpha plus I sin 2 alpha into cos 2 beta plus I sin 2 beta is equal to cos theta plus I sin theta. If you just multiply this and equate real part with real and imaginary with imaginary, you will be in a position to solve this. And I hope, see this cis alpha is nothing but cos theta plus I sin theta. This is the short form of representing cos theta plus I sin theta. Don't get confused. Okay, cis theta or cis alpha is nothing but cos alpha plus I sin alpha. You can take a screenshot of this. Yesterday, I was mentioning some problems which I have given in the practice questions, right? I have told you to go with some method which will give you a solution without any confusion, right? I just wanted to give the solution. You can recheck your answers, what you have calculated. Please look into this, children. You can go for a screenshot of this problem. One problem is multiplicative inverse of I power minus 35. I have taken up that problem in two different ways. Of course, if you are striking with the idea, the second one can be taken directly, or the first one as usual. I power minus 35. I am reducing it as I square whole power something into I, right? So, and the remaining thing I think you can follow. You can please take the screenshot. In the second method, the only change what I have taken is I power minus 35. We are writing it as I power minus 36 plus 1. Why this 36? See, 36 is a multiple of 4. When I have I power 4 is 1. So directly 1 power 9 gives me 1. So this is one of the style of doing the problem. Then the next problem what I was mentioning is when you are given with z is equal to 3 minus 5i. Then you are asked to show that z cube minus 10z square plus 58z minus 136 is equal to 0. Now this problem, see, whichever method you follow, it's okay. But only thing is, if you go by this method, you can avoid mistakes. Okay, I have taken z cube separately, then 10z square separately, then 58z separately, and then we have substituted this. You can take the screenshot for this of this problem also, children. Thank you all.
Thank you, Usha madam. Thank you for a wonderful explanation about Modulus amplitude form. Children, madam has also given you the solutions for the previous practice problems. Please make a note of that. And if you want, you can revisit the same session and clarify your doubts. Thank you, Usha madam, for a wonderful session. Thank you.
Thank you, madam.